All right, look at that. Okay, so so thank you all for coming to the second undergraduate math seminar. Today we have our own former Pitt math graduate student, Cezar Lupu. He was at the University of Pittsburgh for quite a while, even during my undergraduate and graduate career. He helped me a lot. So it's really cool to see him here. And he is going to give a talk on the Riemann hypothesis, but not a proof of it, I don't think, because we only have an hour. So maybe just a problem that's equivalent to the Riemann hypothesis. Involves some harmonic numbers, some logarithms, exponentials, stuff like this. So so Cezar, I will leave it to you.
All right, thank you very much. Let me just start sharing the, wait. I cannot oh, yes, I can. Okay, sorry about that. Okay, so today I will talk about, like I said in the abstract, my absolute favorite paper from the monthly. I remember when I was an undergraduate, when I saw this paper for the first time, although when I was an undergraduate, our access to the American Mathematical Monthly was quite limited. But anyway, somehow I managed to put my hands on this paper, and I remember I was very fascinated because it was so an elementary restatement of the famous Riemann hypothesis. So basically, just like the title says, let me just dive directly into the subject, and the following problem. So let's write, and I'm gonna use this E from the elementary is the following. So let me write it like this. Sigma of n, which is the sum divisor function, is less or equal than hn plus e to the hn times natural log of hn for all n greater or equal than 1. So let's consider the following elementary function, the following elementary inequality, sorry, right? As you can see here, and let me just, so this guy is sigma of n is the sum divisor function, right? Well, you learn about this in any elementary number theory course. And Hn is the harmonic number or harmonic sequence. Again, this is done basically in any introductory analysis course. Well, if you look at this statement, it looks very simple. Well, almost like a homework problem, but the problem is that this elementary problem, and I'm just going to say directly the main result, so theorem, which is due to Lagarias, and this goes back in 2002. Anyway, it was published on Archive a bit earlier, but I'm just going to put the year that it appeared in the journal. And the theorem says the following. It says that problem E is equivalent with the famous Riemann hypothesis. That's his theorem. In other words, well, solving this problem is nothing else than just solving the Riemann hypothesis. It's if and only if. Well, I put here E because it stands for elementary, but maybe I should put, just like Lagarias says in his paper, maybe I should put an H for hard, because it's still unsolved. Well, we will see. In fact, in today's lecture, I'll prove this. The proof is not that hard, but I'll rely on on another result, on another statement which is equivalent to the Riemann hypothesis, And anyway, as we proceed, you will see exactly what I'm talking about. But before we start talking more in more detail about this theorem, I would like to say a few words about the Riemann hypothesis as much as I can. I don't want to dwell too much on it because I want to keep the talk as elementary as possible. But anyway, the Riemann hypothesis, let me talk a bit about this. So the Riemann hypothesis well, it concerns the zeros, and when I say zeros here, I mean the non-trivial zeros of the Riemann zeta function. And this Riemann zeta function is defined in this way by this absolute convergence series, the sum from 1 over n to the s, and this s is a complex number whose real part of s is greater than 1. So that's the famous Riemann zeta function. Well, it was defined by Euler for real exponent, and then Riemann in his famous paper, well, in fact, I should say this, in 1859, Riemann, in his, I would say, without any exaggeration, this is one of the most important papers ever written in mathematics. I mean, and I stick to my statement. He considered this function, and in fact, he proved many things. Well, he proved, among many other things, that prove that zeta of s can be extended to the whole. Okay, can it be? Okay, let me just say it. Bianalytic continuation, whatever that means. To the whole complex plane. Except s equals 1. Well, this is a pole with residue 1. Anyway, I don't want to get too much into details here, but this is one of the things he proved. Another thing he proved was, well, like I said, he proved the functional equation, where he also derived a functional equation for zeta of s, and from this function, and also the trivial zeros. And the trivial zeros follow immediately from this functional equation. And zeta of negative 2k, these are the trivial zeros. But also there is something, there was a question there about the non-trivial zero. So the question is, so what about the non-trivial zeros of zeta of s? That is the question. Well, that's actually the Riemann hypothesis, which basically says the following. And like I said, for me to talk in more details about this, probably it will be a big part of any complex analysis course. So the Riemann hypothesis says that non-trivial zeros, or non-real, I would say, but anyway, let's, of zeta of S have satisfied this, have all real part of S greater to 1/2. That's the Riemann hypothesis. Anyway, why is this so important? Why is the Riemann hypothesis so important? Well, it's very important because it has at first, just at first glance when you look at it, it has tremendous consequences to, I don't know, distribution of prime numbers. It's very important. And I'd like to explain a little bit about this. For the distribution of prime numbers. And I would like to explain something about the history of this, because this is why people were people were very interested in it. But before I even explain about this, let me just talk a bit about the distribution of prime numbers. And now I'm gonna define the following function, the prime counting function. And I'll explain immediately how the Riemann hypothesis is connected to this function. The prime counting function, which is defined by this, pi of x, right? So basically, it counts the number, the number of prime numbers greater than 1 and less or equal than x, right? This is the prime counting function. And what we know, and I will again go back into history, Gauss was the one that empirically, Gauss observed that this pi of x behaves, well, let me just say in words, maybe I should be a little bit vague. Observe that pi of x is approximated, let's say, why not? Well approximated, as he said, by this logarithmic integral, well, from integral from the 2 to x of dt over log t. Anyway, some people define from 0 to x anyway, it doesn't really matter. Which itself, this guy, well, this is a very elementary exercise. This guy satisfies, let me, that Li of x is, well, it's x over log xn plus some error term of x over log x squared, I think, something like this. Anyway, that's this is what this logarithmic integral satisfies. And now the Riemann hypothesis. Okay, and before I even let me remind you, a big result back in the day was the prime number theorem. In fact, in the late 1800s and even after that, they awarded even a Fields Medal for anyone who could find like a real elementary proof of the prime number theory without using complex analysis. But anyway, this happened in 1930s. The prime number states the following, that pi of x is asymptotically x over log x as x goes to infinity. In other words, this, for me to explain this, this means that the limit as x approaches infinity of pi of x over x log x is 1. This is the prime number, the prime number theorem, and in fact it will give you a very nice asymptotic, if you want as an exercise to look at the nth prime number, it will give you a nice asymptotic estimate for that. But anyway, that's not the purpose of our talk. Well, this is, like I said, this is the prime number theorem, but the Riemann hypothesis, and from now on I will abbreviate Riemann hypothesis with RH, so that so we'll abbreviate with RH. The Riemann hypothesis is equivalent with the following how should I call it? Qualitative estimate of the prime counting function. And I'm just gonna write it in this way: pi of x minus is less or equal than a constant, which depends on epsilon, times x to the power 1/2 minus epsilon. So this is what, well, I think it's plus here. Yeah, okay. This is what what Riemann hypothesis gives you. But anyway, and I would like you to compare this to the following result of Vinogradov and Korobov. I think it's 1958. I remember I was trying to read their paper. They give up what they will give a prime number theorem. So with error term. Which says the following, that pi of x minus that logarithmic integral is less or equal than, we have a constant times, oh my God, if I remember there. Anyway, it was something like C1 times x times some exponential here, that of another constant, C2, let's say, times, well, something log of to something here, epsilon. I don't remember the exact, some constant here, minus epsilon. Anyway, so this is a weaker version of the one that you see above. So this is, of course, the C1 and C2, they both of them depend on epsilon. But anyway, I don't remember exactly their result. They have some constants here, I don't know, 2/5 or something like this. Anyway, I don't remember. So this is, as you can see, it's a prime number theorem with error terms. Anyway, this paper was improved by some guy, I don't know, Steining, back in the 80s. I think it was published in a paper in Invenciones. He actually improves the result of Vinogradov and Korobov. And both, well, I don't remember how Vinogradov and Korobov proved this, but I know for sure that Steinig's proof was quite elementary, I would say. All right. So this is a little bit about the Riemann hypothesis and its equivalences, and I would like to see a comparison between this and prime number. But now in a different setting, and I will get closer to our purpose to this talk, is that there is another equivalence which was proven by this guy, Guy Robin, in 1984. He proved the following, proved that the Riemann hypothesis is equivalent with the following. In fact, because I will use his results. He proved that the Riemann hypothesis is equivalent with the following inequality: sigma of n. Well, sigma of n is the sum divisor function, as we have seen above, is less or equal than e to the gamma times n log n. That's simple. But starting from n greater or equal than 5041, that's what he proved.
And Cezar,
Yes.
what is gamma?
Okay. Gamma here, yeah. Gamma is the Euler-Mascheroni constant. Right, some people define it using the harmonic number. Anyway, I'll define it this way. So there's a fractional part of t over t squared d. Okay. But anyway, starting from this, you can just by breaking that integral into like step integrals, you'll find the exact. You can write this gamma constant in terms of the harmonic sequence. Anyway, we'll get there. I'll explain the details immediately.
Okay, thank you.
So this is what Robin proved. So I'm going to pronounce his name in this way so that I will emphasize the fact he's French. In fact, I was trying to read his paper. I couldn't find it. Anyway, he proved this. And in fact, he even has something well, basically what he tried to do is to improve a result of Groundwaters, and I'll explain immediately. And now I would like to explain what about the following question I want to address. I would like to see some asymptotics for sigma of n, for the sum divisor function. So what kind of estimates do we know for sigma of n? Well, of course, you can say those elementary estimates, but I want to dive more into details here, something more serious. And the first result, if I remember, was concerning about the average size of. So the first one is the first result. I think due to Bachmann. Proved an estimate for the basically he gave an asymptotic estimate for the average size of sigma of n. And what he said, his result was the following. And okay, let me mention in the following theorem. He proved the following, that the average size of this is nothing else than pi squared over 12 times log n. Log n was, I think it was n anyway, plus some error term, O of log n, something like this. But anyway, so this is the first result. But now in 1913, this is Groundwaters came with another result, which is a little bit closer to the result of, if you look here, to Robin. In fact, I would, well, let me mention the Groundwaters. Basically, Groundwaters says the following: the asymptotic, Groundwaters was concerned about the asymptotic maximal size of sigma of n. And the asymptotic maximal size of sigma of n is given by the following. So just, in fact, let me write it because I want to emphasize this. The lim sup of sigma of n over n log n. Guess what? This is e to the gamma. That was the result of Groundwaters. And in fact, if you look at this, Robin proves even more. Anyway, I'm not going to go into detail because I don't want to lose too much time with going into details and explaining the proof of Groundwaters result. But anyway, he uses some asymptotic estimates. Yeah. All right, and now I'm veering towards the theorem of Robin because he proved two results. In fact, I mentioned only one. Robin, 1984, and he proved two things. He proved that sigma of n, I'm just going to write it like this, is less or equal than, and you will see that we will have this error term e to the gamma n log n, and plus here I'll have this number 0.6482 n over log n for all n greater or equal than 3. So this is what we call unconditional result. Doesn't depend on Riemann hypothesis, but as I mentioned above, Riemann hypothesis is equivalent with sigma of n is e to the gamma n log n for all n greater or equal than 5041. Okay, as you can see the difference. So that was his striking result that he proved in 1984. Anyway, and in fact, to prove Lagarius' theorem, we'll dwell on this. Well, it's kind of, Lagarius is, I would say, honestly, Lagarius is a modification of Robin's theorem. And now, well, I want you to look at it. It's pretty amazing how simple can Riemann hypothesis can be restated, right? Anyway, but I want to say a few words about what he actually proved in his paper, because he actually proved a bit more. So let me talk about Robin's result. Because we will emphasize on these theorems. I want to explain a bit this equivalence here. that the Riemann hypothesis is equivalent to that inequality that you see. And the first result, let's call this theorem. I don't remember the names, I always forget the numbers. Anyway, theorem R1, let's say, from Riemann R, says the following. I want to explain this equivalence a bit in more details. And what he proved was the following, because this is very tricky. This is what how Lagarius speculated this. It was very smart, I would say. This theorem says the following: if the Riemann hypothesis is true, then we have this inequality, right? Sigma of n is less or equal than e to the gamma n log n for all n greater or equal than 5041. Okay, right? But now another theorem that he proved, which is again pretty amazing, R2, if the Riemann hypothesis is false, then there are some constants I don't know, let's say C1 and C2, such that sigma of n will be greater or equal than e to the gamma n log n, right? Plus this, let's say C1, okay, let me write this so that you can see, plus C1 times log n over log n to the power C2. So these are the two theorems. And now, probably as you can guess now, via a couple of inequalities relating maybe this term and the harmonic, so this term and the harmonic sequence, we can get another equivalent statement of the Riemann hypothesis, in fact, of Robin's criterion. So the question now is, and this, how do we relate this expression e to the gamma n log n with hn? That is the question. And I think by this will be covered by the following lemmas, just like Lagarius names it in his paper. We have the following lemmata. So the first one is the following, which is so the answer is given by the following two lemmas. And the first one is, I'm going to write them in this way, is the exponential of hn times natural log of hn is greater or equal than, guess what, e to the gamma times n log n, right? For all, let's say, n greater or equal than 3, I think, yes. So that's the first lemma. Right? And the proof of this is quite, it's not hard, it's very easy, I would say. I would say this is more like a preliminary exam problem. Well, I will anyway, I will modify the proof of from Lagarius' paper to give a shorter one. So instead of dealing with this integrals and all this stuff, I'm just going to say it directly. also, we have this result. Let's say it is well known that the limit, and this is a very good preliminary exam problem, hn minus log n is gamma, right? One can prove that this sequence, let me call this guy here gamma n. Gamma n converges to gamma. Well, it's bounded, it's between 0 and 1. And moreover, this guy is right decreasing. This is very important. Right? Gamma n is decreasing. Is it increasing or decreasing? I think it's increasing anyway. But from here, if you study the it's convergent, of course. And from here, and it follows that that hn will be greater than log n plus gamma. So we have this estimate, right? And once we have this estimate, it's quite clear how we obtain this. We just have to take the exponential, we just have to take the log, and then that's it. It's very easy, right? Well, for the exponential, it's, we'll obtain this first part, right? Then the exponential of hn is greater or equal than, clearly than e to the gamma times n, right? And for the second part, log of hn will be greater or equal if we take the log here and we just neglect is greater than what? Than log n, right? Yes. Okay, that's exactly what we need. So we combining these two gives you a proof for lemma 1. Anyway, it was very simple. This follows from the monotonicity of easily of gamma n. Anyway, in Lagayas's paper is proved a bit differently. The second lemma, now I would like to prove some kind of an upper bound for this e to the hn times log to the hn. And what I prove is the following, but now I want to add something else. I want to add hn as well. And what we'll have is the following. This will be less or equal, kind of the same thing, and log n. And now guess what? This is where the modification comes into play, because if we look back, look at the Riemann theorem, we have this here, this guy, log n, this, I shouldn't say this error, this, and now I will write this in terms of that. So this will be, anyway, it's a constant here. Anyway, I think he put 4, but you can improve it anyway, over log n, right? For all n greater or equal than 3. So that's his second lemma. Okay. Let me explain the proof well in the remaining time. I think I have a couple of minutes. Derek, how much time do I have? I can go till.
Yeah, I think you know, or something. I mean, you can even.
6 minutes, 7 minutes, okay?
You should be good.
Okay. All right. Now, again, I'll what I'm going to do here, I'm just going to modify a bit the sequence gamma. And I'll do the following. So proof. The proof is also quite immediate. So instead of, how should I say it? Gamma prime of n, this, if we define this as hn minus log of n plus 1 this time, again, gamma prime of n converges to gamma. That's obvious. But also by the same consideration, it follows that, anyway, by just starting the monotonicity of the sequence, it follows that that hn minus log n, let me write it directly in this way, is less or equal than gamma. Yeah, and that in the first case it was greater or equal than gamma. In this case is less or equal than gamma. In any case, everything boils down, if you want to look at the monotonicity of these two sequences, you will see that everything boils down to log of n plus 1 minus log of n is between 1 over n plus 1 and 1 over n, which can be proved in many ways. So everything just boils down to that double inequality, so I'm not getting into details. Okay, so this is the inequality I have. Now, taking the exponential, we will have that, the exponential of hn is less or equal than e to the gamma times n plus 1, right? Okay, so I have this, I got this out of my way. And also, now I have to take care of the log part. And now let's look at this, because this is a bit tricky, but not that much. I'll explain immediately. There is a trick that you do here. So we know that now, okay, let me say the estimate. So since hn is less or equal than 1 plus log n, right? It follows that log of hn is less or equal than log of n plus 1. But now I want to estimate this somehow, and I'm going to do something, well, a trick here. And you will see why I'm doing this trick. Usually when you have something log of log n, you're trying to factor something, a log n inside this. In fact, maybe I should write it here. But log of log n plus 1 is equal to, and now I'm going to do the following. So I'm going to force a factor inside here. So this will be log n, and here will be 1 plus 1 over log n. So, and now guess what I'm going to do? Look at this guy. I have log. So this will be less or equal than log n plus 1 over log n, right? Where we use this estimate here, this inequality, log of 1 plus x is always less or equal than x. For x greater or equal than 0. That's what we use. Anyway, so right? And now we multiply these two. Ouch. Anyway, probably I'm gonna, we have the following, the exponential of hn times log of hn. It will be less or equal than, after putting all this together, but anyway, we'll try to neglect this guy. So this guy here, I'll try to neglect it so that I'll have my estimates that some nice estimates. So this guy will be less than e to the gamma n log n. And now this guy plus, I don't want to deal with this, so I'm just going to put something n over some constant, and probably, okay, let me see. Probably this is less than n over 2 log n, probably, but anyway, it doesn't really matter. I can put any constant I want so that everything fits perfectly into the picture. So I will have this, right? Wait. Anyway, and then I'll also use the fact plus the fact that hn, which is less or equal than 1 plus log n, will be less or equal than something that would look like n over log n, so probably n over log n. And adding everything together, it will give me the proof of the lemma. Anyway, it's not hard. But now I want to, in the last couple of minutes, well, I went a bit over time, but it will be the proof of Lagrange's theorem is just instant right now. Because we will use both of these theorems of Robin. Okay, now we have to show that the Riemann hypothesis is equivalent with that inequality, right? Now, the first implication is, suppose that, I don't know, how did I, let me go back a bit to the beginning, see how I, okay, so I meant problem elementary, okay. All right. Suppose that Riemann hypothesis is true. Well, that's immediate. Then we just, by theorem R1 and lemma 1, it follows immediately. So what did we prove? By theorem 1, we proved that sigma of n, well, we said that if Riemann hypothesis is true, then this guy is less than e to the gamma n log n, which is less than by lemma, so this is R1, and this is lemma 1, which is less than hn. Well, it's actually, I will add this hn just for free, because we proved that it's, we proved only that this guy here, e to the hn times log of hn is greater than e to the gamma n log n. All right, so it follows. That was immediate. But this is for all, pay attention here, for all n greater or equal than 5041, because R1 started from that rank. Anyway, the cases from 1 to 5041 can be verified by a computer. So it's, and as Lagrange states in his paper, it's actually it verifies. And now the other implication, oops, we want to prove that, well, we want to prove that that inequality okay, so we will assume that, in fact, we want to prove that if that inequality holds, right, the Riemann hypothesis is true. So suppose by contradiction that is false. Right? And now we keep in mind that we have a theorem R2. By theorem R2, we have that estimate. If the Riemann hypothesis is false, then we have that estimate, right? By R2, and by the way, I think I forgot to say something here. Which is very important. And this, such that for infinitely many n. I forgot to say about this, and this is very important. Oh. Anyway, if the Riemann hypothesis is true, then this estimate will contradict then by theorem 2. In fact, let me say directly, the inequality will contradict the estimate from lemma 2. Anyway, then that's it. That's the proof of this. It's immediate, and like I said, as you can see, it relies on Robin's theorem. And in fact, I would like to just one more minute to tell you there was a problem. In fact, you can prove that sigma of n is less or equal than hn plus 2 times the exponential of hn times log n for all n greater or equal than 1. You can actually prove this, but the question is if you can lower this constant 2 to 1. Well, I think I long time ago when I was an undergrad, I think well, using some approximation formulas, I lowered it to 1.09, something like this. But anyway, I'll stop here. Thank you very much.
All right, thank you, Cezar.
Anyway, it was a bit technical. Maybe it wasn't supposed to be like that, but I wanted to tell you about this paper. It's a very nice paper.
Yeah, that was a great talk. So we might have time for like one question if someone really wants to ask a question. Then Cezar is here. So any questions? Okay. Yeah, just for the sake of time, I think we're gonna stop here. So thank you, Cezar. Let me stop the recording.